All right, folks, we are going to talk about static electricity today. Now, before we get started, a couple of things to take note of. First off, you should be following along with the student-paced Nearpod. So if you go on to Schoology and go into Notes and Nearpods, you will see a Nearpod for static electricity. I want you to click into that one. Do not use the code that is displayed on this screen. It will not, you will not be able to follow along. Second, you will be taking notes just like you would with a normal lecture. However, the main difference here is that you can pause at any time so that you can catch up. So I'm not going to take the normal pauses that I do during lecture. That is your responsibility to do that. Please do the interactive parts as much as you can. I will be able to gather information from those so that when we meet next, I will be able to answer any questions or address anything that you all would like me to address. So let's go ahead and get started talking about static electricity. Our learning target for today is I can explain the relationship between electric charge, static charges, electric force, and electric field. Your notes, you need to go ahead and set up your notes in your yellow packet. Our essential question today is what is electricity? And we have 4 guiding questions. What causes an electric charge? How do electric charges interact? What are the differences and similarities between electric charge, electric force, and electric field? And what are the 3 ways that static charge is released? So, we are going to be looking at some simulations on PhET going forward, and during the following simulation, please pay attention and make observations. I want you to play around with the simulation and see what you can do, and then I want you to be prepared to share out at least one observation afterwards. So this should be on your screen right now, and what you can see is that we have a balloon and a sweater here. So balloon's right here, sweater's right here, and then there's a wall over here. And what you can do with this is take the balloon and move it around. And what I want you to do is make sure you have all of the charges shown, and go ahead and move the balloon over here to the sweater and see what happens. And you'll notice that the charges transfer. So you can release the balloon, you can see what the balloon does, you can have 2 balloons and do all sorts of things over here, and you can make observations. So go ahead and mess around with the different settings on here, and when you're done exploring this, go ahead and continue this video and continue taking notes. So go ahead and tell us something that you observed during the balloon simulation. You can post it here, and then read through what other people noticed as well. Hopefully this populates with a bunch of student thoughts about what we see with the balloons. So our focus, as we said before in our essential questions, is charge, or electric charge, the difference between electric charge, force, and field, and 3 ways that static charge is released. So one thing we need to remember as we get into this is we need to go back to our thoughts about subatomic particles. We have 3 subatomic particles. Protons have a positive charge in the nucleus. Electrons, a negative charge orbiting the nucleus, and neutrons have no charge in the nucleus. So, quick poll. An atom becomes an ion when it gains or loses which subatomic particle? Go ahead and pause and enter your answer. Atoms become charged when they gain or lose electrons. So, electric charge is going to be a property determined by the number of protons and electrons in an atom or group of atoms. If we have a negative charge, that means that there are more electrons than protons. If we have a positive charge, that means there are more protons than electrons. Please note that we've got these in all capitals. That means that these are vocab terms. If you take a look in your packet, you will see a vocab section for for static charge and or static electricity. So you have these already defined, but make sure you're doing the drawouts as well. we are going to be focusing on the electrons and movement of electrons in this unit. So let's start with what electric charge is. And this is something that is we measure in units. And the metric unit is a coulomb. And a coulomb tells us how much electric charge there is in a system. So you can think of a coulomb, or a coulomb is to electricity as a liter is to water. A liter tells us how much water there is. A coulomb tells us how much electricity there is. And a coulomb is a very specific amount of electrons. 1 coulomb is, let me see if I get this right, 6 quintillion, 241 quadrillion, 509 trillion, 629 billion, 152 million, 650,000 electrons. It is a lot of electrons. Luckily, you do not need to remember that number, but just be aware that it is a lot of electrons. Now, electric force is different than electric charge. Electric force is the attraction or repulsion between electrically charged objects. So once you have an electric charge on an object, and that object is interacting with another electrically charged object, that is going to be an electric force. Now, with electric force, opposites attract, and like repels like. Just like magnets, the opposite sides of magnets will attract, and like sides of magnets will repel each other. So that means 2 positive forces you see here are repelling each other, and a positive and negative force or charge would be attracting each other. The force increases as the charge increases. So you see this right here in this part of the image here, that if you just have single positive charges, there's a small repulsion between the two, but if you double that charge, that is going to massively increase the amount of repulsion between the two. So as you increase the charge, the force between the two increases. The force decreases as the distance between the charges decrease. So these 2 charges are close together, so they're very strongly repelled. These 2 charges are farther apart, and so they are less repelled from each other. This concept of how charges are attracted or repelled to each other and the relationship between the amount of charge and the distance is called Coulomb's law. So, if we go ahead and go back to our simulation, and I encourage you to try this along with me, what we can see is we go ahead and rub our balloon here, and the balloon picks up all of the electrons from the sweater. Now, if the balloon is very close to the sweater and we release it, it goes really, really fast to the sweater. However, if we move it further away, it takes a little bit longer for it to go. And if we remove the wall there, it takes even longer. That's because it starts out really slow when it's over here, and therefore it takes a longer time, or it's slower because the force is not as strong. When it's really close, it snaps immediately. And so that's Coulomb's law in practice. We can also reset the balloon and have 2 balloons and give them approximately the same charge. So I'll get half of the electrons on here, and then I'll get half of the electrons on this balloon. And you'll see that these 2 balloons now are repulsed by each other, and if they're closer together, they're more repulsed by each other. So right now they're kind of just a little bit, but if I get this balloon right up here, it's going to go real fast. So that shows stronger charge, and now that balloon is being kind of pulled towards the positive charge on the sweater, and then being repulsed by the negative charge on this balloon. So kind of what you're seeing there. Mess around with that, see how you can make the charges interact with each other, with the difference between how much charge there is and how close or far apart they are. Electric field is our third concept when it comes to static electricity. An electric field is the space around an electric charge that affects another charge. And this is going to be how we diagram this. This is one positive charge and one negative charge next to each other. And positive charges produce a field that points away from the charge. So you see these arrows from the positive charge are pointing away, and the negative charge produces a field where the charges are pointing towards it. So that means that charge moves from the electric field moves from the positive charge to the negative charge. And the field is stronger where the lines are closer. So what you'll see is that all of these are connected. So these arrows all transfer from the positive to the negative, but these ones that go off the screen, they actually loop around up here and go over to the negative as well. So even this one that's over here, it's making a big loop around and coming back over on this side. What you'll see is that where the positive and negative charge are closest together, that's where the lines are closest together, meaning the electric field is strongest. As you move to these parts where the electric field is kind of farther away from the negative charge, the lines are farther apart, meaning the electric field is weaker, which is what you would expect. The parts where you have the charges close together, it's very strong. Where they are not close together, they are farther apart and weaker. So, I've got a clip here. I'm going to ask that you pause this video and watch this clip. It is from the 1990s sitcom Seinfeld, and I think that it's a pretty relevant clip to what we're talking about. So go ahead and pause that, and then pause this, watch the video, and then come back to this lecture. So from that video, what I hope that you kind of see is that opposites attract. You know, we might always think that or two things that are like each other will attract, but kind of in life, you see that if things are too like each other, they will repel each other, and we kind of make that metaphor to electricity. So what I would like you to do in your notes now is create a Venn diagram that looks like this. And over each of these, I would like you to go ahead and put electric charge, electric force, and electric field. And take a moment, and I want you to go ahead and fill this out. This is something we're going to do when we gather together next. And we'll use this as kind of a review technique. But if you already have this done with some ideas in there, it'll make this much more valuable and useful. So go ahead and fill this out to the best of your ability, and we will come back to this when we're together as a group. So, static electricity and charging. Static electricity is the increase of electric charge on the surface of objects. Static electricity explains how charges are transferred from one place to another. Now, static electricity or charges can be transferred in three ways. Friction transfers electrons from one object to another. So in this case, when we were rubbing the balloon against the sweater in the PhET simulation, that the balloon wants electrons more. The rubber in the balloon wants electrons more than the wool in the sweater, and so the balloon takes electrons away. Contact transfers charge as well. And hopefully we'll have a Van der Graaf generator set up front so you can see when an electric charge builds up and you touch the generator, the charge transfers to you through contact. Induction is when there is a transfer of charge without contact, and that's going to be like if you were to shock your finger on a doorknob in the winter. That is because you don't even touch the doorknob, yet you still get shocked, so there is a transfer there. So, static discharge is a sudden movement of charged particles, and you can see this in lightning. That's a bunch of charge builds up in clouds, and then there's a sudden discharge of static electricity, and the same thing with a shock from a doorknob. A lot of electrons got transferred to you. You touch the doorknob, and those electrons jump to the doorknob, causing a shock.